We are live. Oh my gosh. I think Suji has made some sort of discovery. There are some leaves falling because of fall time in the garden. And she was napping and taking rest. But now she is up and having a little bit more of an active period of time in this afternoon. It's a brilliantly sunny day. Hi, Fuji. Could we not push this? So lately, Fuji has been pushing the auto feeder. They just got their snacks. So it's a way in which he acts out. But we will come over here and look at Baji. Hi, Baji. Hi, Baji. Hi, Baj Baj. I just wanted to have a quick chat today, actually, and do a longer live later on. But here we are to show the kitty cats briefly. So thank you for joining. Let me try to do the thing that makes things slightly better for us with Fuji here and his auto feeder. Hi, not your average cat. Hi, Fuji, please don't do that. He actually kind of got us away from the window and over here, which is unfortunate because we were having a good time at the window. Let's come over here, Suji Mama. There we go. Yes, we can relax over here and have a good afternoon like a good kitty cat and just have a chill time, sunbathing, enjoying nature, soaking in the sunshine. And enjoying life. I'm trying to see if I can share my live, but maybe not. Oh, there it is. I think I can. I'm trying to see if I can. There it is. If I hear my voice twice, I know that I found my live on the channel. So I'm letting our friends know that we're live. I'm still recovering from my birthday celebrations last night. So that's why we're a little bit tired and we're a little bit late today. But yeah, here we are. How is everybody doing? Hi, Salam. Hi, not your average cat. Hi, Salam. Hi, everybody. Hope you had a fun birthday. Yes, thank you. Yes, my friends took me out and we had a really nice time in Boston. We were in the heart of Boston doing dinner and drinks and at some restaurants and bars, and it was a really happening night. Lots of people out, and we were even followed by a homeless guy for a little bit, so it even felt a little bit, I don't know, risque or dangerous. But we were together, and I made sure we walked each other to like our cars or got rides back properly. So we went home safely because we were out late. So it was kind of wild in that sense of like a nice birthday celebration, but we were catching up and talking until late. So then we got home and decided that Sunday we have to take it a little bit slow, like a kitty cat, and enjoy the sunshine and sunbathe and recover and sit in the sun. Hi. Hi, Salam. Hello, hi. And hello, what is from? Interesting usernames, and thank you for being here. Yeah. So that's what's going on. Thank you so much for joining. That's the aftermath of the birthday celebrations. So I've been meaning to get myself a mic because I think that would help with some of these discussions and book reading and physics learning easier. But until such time, I will continue to use whatever I have. So anyways, I have been covering topics from a book called Einstein's Cosmos by Michio Kaku. Hello, I'm back. Hi, how are you? Hello. And I wanted to real quick cover something from the book and then call it a day. Good. Okay, very nice. Hi. Callie says good. Tosca Van Son. Kayla, hi. Hi. Good to see our regulars here. And if we missed you, sorry about that. But good to see our VIP guests, some of them in the live chat. Thank you so much. Feel free to dominate the chat. My phone is being taken off again when my mom calls me. Is this the phone that you're going to be losing anytime now, Kayla? That is a sort of exciting, I guess it could be happening any moment now. I got you. Well, you know what? We're going to be learning about physics, so maybe she'll let you keep it. So it's like, it's going to be like a class now. So let me get started actually, because I'm a little tired. So we're going to be talking about physics. So last time, look, we read up to this page, which is page 46 of Einstein's Cosmos by Michio Kaku, and we were talking about special relativity. So we saw that Einstein had a really good year. He was kind of struggling with his career and getting assistantship and sort of getting a nice job at a university. With the help of his friend, he ended up working at the patent office. So not exactly the most amazing academic career, but then he was keeping up with the work that was going on in the world of physics, which was really good because, you know, he kept up with it, and on his own, and by doing the research and by working together with the study group and sounding off of other colleagues and friends, he actually ended up having a really good year of contributions that he made to physics, including but not limited to probably the theory of special relativity, which talked about the relative time the relative nature of time and space, things like length contraction and time dilation, depending on the speed at which you were traveling and your frame of reference. So this was theory of special relativity. He also worked on mass energy conversion. So an extension of that theory of special relativity was to show that mass and energy can convert to each other. So energy conservation law was sort of being contradicted. Then he ended up also working on photoelectric effect. Some work had already been done to show that if sunlight was shined on metal, sometimes we got electric currents out of it, very similar to how we have solar panels now giving us electricity. But then Einstein contributed to this topic by showing that actually light, the way this works is that light is made up of particles called photons or quanta of light. It got the name photon later on, but he drew from quantum mechanics theory by Max Planck and suggested that perhaps light had a dual nature of not only wave nature, but also particle nature. And in fact, quanta of light had energy that was proportional to the frequency of light. And this could be shown by basically shining the light on metal and then measuring the voltage of the current that would come out of that metal with light basically causing electric currents to come out of that metal, like basically giving energy to electrons and then forming an electric current. But then to prove that light was basically quanta of light having certain energy, like packets of energy, and that packets of energy was proportional to the frequency of light. Well, you could change the frequency of light and then show the corresponding change in the voltage that you would get out of the metal, which would be from the electric current that was created in the metal. And that electric current's energy, which was coming from light, would then give us that light's energy was proportional to its frequency, which was also kind of contradictory to what Newtonian mechanics might tell us, which would have suggested that it was the intensity of light that affected its energy, not its frequency. So this was also a fundamental contribution of Einstein during that same year. Very productive year indeed. And during that same year, this is what he got his Nobel Prize for. So although Einstein is more famous arguably for his theory of special relativity and general relativity, this is actually, oh, thank you, Kayla. This is actually what he is given the Nobel Prize for in the year 1905 because of photoelectric effect. And because photoelectric effect was understood a bit better, I think, by people. It was more understandable by people because it was also a more direct application in our daily lives, such as even now, this whole application of solar panels is only possible because of the photoelectric effect. If we didn't know how to control, how to have light shine on metal and create electric currents in the metal and give us electricity in our homes, then the solar panel concept wouldn't really work. But if you couldn't show that in physics experimentally by showing exactly how, with the frequency of light that can shift, the energy you are receiving out of the metal panels, then it wouldn't really work, right? It would be a mystery. So Einstein solved that mystery. He suggested the application in the first place and also showed it. So anything in physics that can be demonstrated in the lab experimentally has a ton of value. Sometimes theories are proposed and they cannot actually be verified experimentally for a very long time, such as special theory of relativity and general theory of relativity were a little bit more abstract and they could not be as easily shown. Special theory of relativity still could be shown pretty easily, but actually direct evidence of the general theory of relativity, it took many, many more years. It was actually more recent. in the last decade or so that we got more direct evidence of gravitational waves and the general theory of relativity's suggestions. So not all theories are equally lucky in how well or how easily and how quickly they can be demonstrated. So this must be kept in mind when we talk about these great inventions and great work of great people. Sometimes they die before their theory is actually proved, which is pretty sad. But at the same time, it's not sad because these people who work on these things are happy because they're working on those things, not necessarily because of the results and applications that they would see the next day. So sometimes you actually do great work and it's not verified for a very long time. But it was actually a very exciting thing during my graduate program in physics at Ohio State. This was in the last decade because I'm not that old, even though pretty old, that we actually saw direct evidence of gravitational waves, and it was a very, very big deal, I can tell you. So 1905 is the year we're in this book right now. You will see that general theory of relativity was a little bit later, but it wasn't until something like 2015 or so that we got, so 100 years later or so, is when we got direct evidence of his general theory of relativity. So relativity, even though that's what made him famous eventually when he was older, is not what he was probably the most recognized for right away. He was recognized for his photoelectric effect. And then actually, I forgot to say, there is still one more thing he did during that same year. We've mentioned 3 things so far. The length contraction, time dilation, so relativity of space-time, energy and mass conversion, E equals mc squared, which is also used destructively, such as in atom bombs. Probably not an intent of Einstein. Third, the photoelectric effect. And also, fourth, a demonstration of Brownian motion was also all contributed by Einstein during the same year. So we'll read a little bit. We'll read a little bit from this page that might summarize some of these things that I've been saying. 1905 was truly an annus mirabilis in the history of science. If we are to find another comparable miracle year, we would have to look back to 1666 when Isaac Newton, 23 years old, hit upon the universal law of gravitation, the integral and differential calculus, the binomial theorem, and his theory of color. So, quite truly, after 1666, which is a long time ago, a couple hundred years ago from this point, probably after 1666, it was really 1905 that we saw something as miraculous of a year in physics as what we found with Newton. Because remember, Newton was a great physicist and also a great mathematician and also a great experimentalist, actually. And he independently invented calculus, which is a very big contribution. It actually made all of this math stuff possible for both physics and math applications. And he wrote about this in his Principia books. So that's why it's so important to publish your work when you do significant work, especially to have them be peer-reviewed and also published, because that's actually how you preserve and propagate your work through the centuries. So because he had the Principia books, we still know, or we can still learn about what he did back in the day. And also because of the ability to print. Of course, before we had printing, we couldn't publish as easily and distribute our publication as easily. So a great big thing we should be thankful for nowadays is our ability to publish and distribute publications much more easily thanks to the internet. Anyway, so Einstein had to submit his contributions, for example, in written papers like we mentioned in this chapter. But we'll summarize real quick. Einstein had finished the year 1905 laying down the photon theory, providing evidence for the existence of atoms, and toppling the framework of Newtonian physics, each of them worthy of international acclaim. He was disappointed, however, in the deafening silence that ensued. His work, it seemed, was totally ignored. Disheartened, Einstein went about his personal life, raising his child and toiling by himself at the patent office. So, patent office is where he worked, remember, when he's doing all this great work. He didn't even have really a university proper position at this time. Perhaps the thought of pioneering new worlds in physics was all a pipe dream. In early 1906, however, the first glimmer of response riveted Einstein's attention. He just got a single letter, but it was from perhaps the most important physicist of the time, Max Planck, who immediately understood the radical implications of Einstein's work. What drew Planck to the theory of relativity was that it elevated a quantity, the speed of light, into a fundamental constant of nature. Planck's constant, for example, demarcated the classical world from the subatomic world of the quantum. We are shielded from the strange properties of atoms because of the smallness of Planck's constant. Similarly, felt Planck, Einstein was raising the speed of light into a new constant of nature. We were shielded from the equally bizarre world of cosmic physics by the huge value of the speed of light. So that's really nice. That even somebody like Einstein, it's not nice, it's nice, but also a little bit scary, that even somebody like Einstein was actually not recognized. You know, because when you do great work, you actually need equally great people to recognize your work. You need great peers to peer review your work and to recognize and understand your work. Thankfully, within a year or so of his great contributions in the year 1905, he got recognition from a great scientist of the time, Max Planck, who you'll remember was basically a father of quantum mechanics. The entire field of quantum mechanics, with Planck's constant and all those concepts of basically quanta, of energy, the concept of quantum, you know, versus classical mechanics, was created or contributed to heavily by Max Planck. So, of course, this was a clever person. And it took such a clever person to realize the potential of somebody also clever like Einstein. So we must remember that sometimes we do great work, but it might take time for it to really take off because it still has to be reviewed and understood by people, maybe even great people, for it to be appreciated properly. In Planck's mind, these two constants, Planck's constant and the speed of light, laid down the limits of common sense and Newtonian physics. We cannot see the fundamentally weird nature of physical reality because of the smallness of Planck's constant and the immensity of the speed of light. If relativity and the quantum theory violated common sense, it was only because we live our entire life in a tiny corner of the universe, in a sheltered world where velocities are low compared to the speed of light and objects are so large, we never encounter Planck's constant. So that's another great sentence to summarize that also what we found with Newtonian mechanics being so sustained for so long and so correct, and even now it's correct in the realms of classical pictures. Newtonian mechanics or classical mechanics holds true in regular everyday world where we're not dealing with scales that are so small as in quantum mechanics, or scales that are so big as in cosmic scales. In cosmic scales, you need relativity. In very small scales, you need quantum mechanics. In the everyday life in between, you need classical mechanics, which is Newtonian physics or Newtonian mechanics. And that's why he was correct for so many centuries. And even now, Newtonian mechanics still holds true to a very large extent, because we're really shielded from the very small and the very large. And the very small and the very large are basically given sort of represented by these constants of nature, such as Planck's constant, which is so tiny, and the speed of light, a constant that is so big. You should, if you don't know the speed of light, by the way, you should Google it, and then you'll know how big it is. Hi, Sanjana. Hi, Jason. Hi, Kayla. So, nature, however, so we might live in a world that is sort of Newtonian mechanically okay, but nature is not just our world. Nature is also the very small world, and nature is also the very big world. So, nature, and there is, by the way, things to learn about both those worlds still that we still don't know, even now. We still have a lot of questions about the big world where relativity is more relevant, such as the question of dark matter and dark energy, are big questions of science, even now that we don't have answers to. And there's also questions about the very small scale world, like quantum mechanics, that we also still have questions to, that we still don't know. It's been difficult to get answers sometimes in these other worlds because of the very different scales in these worlds, and they're not really our scale, like human being life scale. Like we live in neighborhoods that are in countries that are on the world, that is in a solar system, that is in a galaxy, that is in a part of the universe that's really quite tiny, you know? The galaxies or galactic scales are much, much bigger. Or cosmic scales. That's what I mean by cosmic scales. So, on the scale of like a house or our life, Newtonian mechanics is just fine. On the scale of galaxies, it's not just fine. We need relativity. And even with relativity, we might have questions that we don't fully understand, such as the nature of dark matter. So that's what I mean. It's difficult, but nature is more than just our world. Nature, however, does not care about our common sense, but created a universe based on subatomic particles that routinely go near the speed of light and obey Planck's formula. So yeah, that's another point, is that very tiny particles can actually travel close to the speed of light. They do not travel at the speed of light unless you're a photon, which is light. But there can be very high energy little particles. My PhD was actually on that. So there can be low energy tiny particles, there can be medium energy tiny particles, and there can also be very high energy tiny particles. These tiny particles are not massless like light or photon, but they can be very light. For example, the neutrino is a little tiny particle that can be made in various nuclear physics phenomena, as well as particle physics and astrophysics phenomena. And we're still learning about them, actually. But we have already learned some things about them, and we have found that they can go very high speed and be very high energy. And so these are the types of scales and worlds, both with how tiny and how big energy, that we would have trouble to connect with, because we don't really exist in those types of frames. Frames as in those types of scales. We don't go that fast. We are not that tiny. You know what I mean? That sort of thing. So in the summer of 1906, Planck sent his assistant, Max von Loo, to meet this obscure civil servant who appeared out of nowhere to challenge the legacy of Isaac Newton. So I suppose now Planck is sending his assistant to further chat with Einstein, because that's who has done such remarkable work in the year 1905. They were supposed to meet in the waiting room of the patent office, but comically walked right past each other because von Loo expected to see an imposing, authoritative figure. When Einstein finally introduced himself, von Loo was surprised to find someone completely different, a surprisingly young and casually dressed civil servant. They became lifelong friends. However, von Loo knew a bad cigar. When he saw one, when Einstein offered him a cigar, von Loo discreetly threw it away in the Aar River when Einstein wasn't looking, as they talked and crossed the bridge. With the blessing of Max Planck, the work of Einstein gradually began to attract the attention of other physicists. So he really needed somebody's blessing before he was taken seriously, because that's just how things are. It's a little unfortunate. But in academia, because, you need somebody clever and established to review, understand, appreciate your work, oftentimes your work can't really take off until you have the blessing of such people. So, anyway, he now had the blessing of Max Planck, which is actually a really big deal because Max Planck had done really pioneering work on quantum mechanics. Ironically, one of Einstein's old professors at the Polytechnique, who had called him a lazy dog for cutting his classes, took a particular interest in the work of his former student. Let me make sure that I focused correctly on this phone here. The mathematician Hermann Minkowski plunged ahead and developed the equations of relativity even further, trying to reformulate Einstein's observation that space turns into time and vice versa the faster you move. Minkowski put this into mathematical language and concluded that space and time formed a four-dimensional unity. Suddenly, everyone was talking about the fourth dimension. So Minkowski did some math as well to reformulate Einstein's observations. This is also actually helpful if somebody else wants to do the math and reformulate or re-investigate your work and be able to present it in a way that people can understand with the math. That can actually be very helpful. Minkowski, as a mathematician, was able to help out with that. And we do study his equations as well in these classes when we take special theory of relativity. For example, on a map, two coordinates, length and width, are required to locate any point. If you add a third dimension, height, then you can locate any object in space, from the tip of your nose to the ends of the universe. The visible world around us is thus three-dimensional. Writers like H.G. Wells had conjectured that perhaps time could be viewed as a fourth dimension, such that any event could be located by giving its three-dimensional coordinates and the time at which it occurs. Thus, if you want to meet someone in New York City, you might say, meet me at the corner of 42nd Street and 5th Avenue on the 20th floor at noon. Four numbers uniquely specify the event, but Wells's fourth dimension was only an idea without any mathematical or physical content. Minkowski then rewrote Einstein's equations to reveal this beautiful four-dimensional fabric. Minkowski wrote, "From now on, space and time separately have vanished into the merest shadows, and only a kind of union of the two will preserve any independent reality." So it's really space-time. It's not XYZ, it's also XYZ and T nowadays, okay? At first, Einstein was not impressed. In fact, he even wrote defense derisively. The main thing is the content, not the mathematics. With mathematics, you can prove anything. Einstein believed that at the core of relativity lay basic physical principles, not pretty, but meaningless four-dimensional mathematics, which he called superfluous erudition. To him, the essential thing was to have a clear and simple picture. For example, trains, falling elevators, rockets. So he liked to get everything sort of solidified in physical reality, whereas mathematics is a way to kind of formalize everything, but that's not necessarily what gives you the intuition or the real physical feeling or reality. Anyway, he thought the math could come later. In fact, at this point, he thought that mathematics represented only the bookkeeping necessary to track what was happening in the picture. So he thought mathematics was like bookkeeping. I kind of agree. Mathematicians like to think of everything with the math, but physicists might think of math as more like the bookkeeping that you need to track everything that was happening, but it was not necessarily the physical reality picture. Einstein would write, half in jest, "Since the mathematicians have attacked the relativity theory, I myself no longer understand it anymore. So that's actually really encouraging. So, like, because a lot of people might struggle with math, but regardless, you can still understand the physical reality of something and the physical concept of something if you visualize and do the thought experiments like what Einstein was doing, like with the trains, the falling elevators, and the rockets. So, since the mathematicians have attacked the relativity theory, I myself no longer understand it anymore, is what Einstein said. With time, however, he began to appreciate the full power of Minkowski's work and its deep philosophical implications. What Minkowski had shown was that it was possible to unify two seemingly different concepts by using the power of symmetry. Space and time were now to be viewed as different states of the same object. Similarly, energy and matter, as well as electricity and magnetism, could be related via the fourth dimension. So, this fourth dimension of time can actually unify more things, electricity and magnetism included. So, there is elegance and use in how Minkowski was formulating special theory of relativity, which Einstein came to appreciate later on. And it's basically, if he had any trouble with it, it's really because different people think differently. Minkowski thought about it in a mathematical way, and certain things can fall out of that can help you with physical reality. Einstein thought of it as a physical phenomena way, and that's how his intuition and his thinking allowed him to understand the topic. So again, don't be discouraged if something is difficult for you. You might just have a different way of thinking about it, is what this is. Unification through symmetry became one of Einstein's guiding principles for the rest of his life. So this sort of symmetry, this sort of like, okay, space, time, this math falling out and the electricity magnetism relation also having more connections fell out of the math. This led him to have hope, not only in power of math, but also in power of understanding more things through the symmetry. And this will come back again when we talk about the grand unification theory later on, okay? Think of a snowflake, for example. If you rotate the snowflake by 60 degrees, the snowflake remains the same. Mathematically, we say that objects that maintain their form after a rotation are called covariant. Covariant, okay? Minkowski showed that Einstein's equations, like a snowflake, remain covariant when space and time are rotated as four-dimensional objects. In other words, a new principle of physics was being born, and it further refined the work of Einstein. The equations of physics must be Lorentz covariant, that is, maintain the same form under a Lorentz transformation. Einstein would later admit that without the four-dimensional mathematics of Minkowski, relativity might have remained stuck in its diapers. What was remarkable was that this new four-dimensional physics allowed physicists to compress all the equations of relativity into a remarkably compact form. So this, by the way, this four-dimensional equation way of writing the relativity equations, that's how it's taught at this point. And even though it might be a little foreign at first for students to get used to this, it is how it is formalized. It is how you have to pretty much get used to it. And pretty much once you are okay with it, it actually does make your life easier mathematically. And that's actually how I suggest E&M should be taught in grad school. So instead of writing electricity magnetism equations in the more traditional way, if you start with special relativity, it actually keeps it a bit more simple, and it also makes you more comfortable with this mathematical way of writing things down, which can then make you more comfortable with more complicated concepts like general relativity. A lot of people don't get to general relativity in grad school because it's too difficult with the math. But if you're used to doing the math in that way, then it would be easier. So everything is about practice, right? Even Einstein needed to learn the math that his physics was supporting, So don't be discouraged. Even Einstein had math issues, okay? For example, every electrical engineering student and physicist, when first studying Maxwell's series of, there we go, this is the sentence. When first studying Maxwell's series of 8 partial differential equations, finds that they're fiendishly difficult, but Minkowski's new mathematics collapsed Maxwell's equations down to just 2. In fact, one can prove using 4-dimensional mathematics that Maxwell's equations are the simplest possible equations describing light. So this is what I meant, actually. I didn't realize this sentence was coming up, which is that once you understand special theory of relativity and its math in this condensed 4-dimensional form, you can rewrite Maxwell's equations more simply. And that might be how you start learning and understanding the concept of light and E&M, electricity and magnetism, which is light, because there's no point in avoiding this anymore, especially in a grad program. There's no point in thinking of electricity and magnetism as separate concepts and spending all this time understanding it when actually it boils down to just light and the special theory of relativity. Might as well embrace it, especially if you've already done the undergrad course. If you get my drift. For the first time, physicists appreciated the power of symmetry in their equations. When a physicist talks about beauty and elegance in physics, what he or she often really means is that symmetry allows one to unify a large number of diverse phenomena and concepts into a remarkably compact form. The more beautiful an equation is, the more symmetry it possesses, and the more phenomena it can explain in the shortest amount of space. Thus, the power of symmetry allows us to unify disparate pieces into their harmonious, integral whole. Rotations of a snowflake, for example, allows us to see the unity that exists between each point on the snowflake. Rotating in 4-dimensional space unifies the concept of space and time, turning one into the other as the velocity is increased. This beautiful, elegant concept that symmetry unifies seemingly dissimilar entities into a pleasing, harmonious whole guided Einstein for the next 50 years. So you'll see this type of symmetry seeking come up with his next work, which is even bigger and even more interesting and path-breaking, which is the general theory of relativity. But this is where I really think, as I've already mentioned, that you need to be comfortable with special. Gaurav says, I'm also struggling in math. That's okay. It's pretty interesting. Yeah. Inspiring, yeah. Being comfortable with the special theory of relativity notation will greatly help with GR, general theory of relativity, okay? So that's why I suggest not avoiding it, especially because it explains light, which is so fundamental. Paradoxically, as soon as Einstein completed the theory of special relativity, he began to lose interest, preferring to contemplate another deeper question, the problem of gravity and acceleration, which seemed beyond the reach of special relativity. Einstein had given birth to relativity theory, but like any loving parent, he immediately realized its potential faults and tried to correct them. So that's the thing too about doing great things, is that it never really stops. You have to do the next thing. It's good to pause and celebrate your great work, but the thing with greatness is that it never really goes away, as in it never really stops. There's always more great work to be done, because the current great work actually gives birth to even more great work. So special theory of relativity is what he worked on in 1905, but then over the next few years, several years, he will go on to work on general theory of relativity, because he realized, well, that special theory of relativity is really only for inertial frames, and it does not explain gravitation, right? So gravitation is something, for example, that causes acceleration. Acceleration means that's not an inertial frame anymore, because inertial frame is what is traveling at a constant velocity. So he realized that not everything, obviously, in nature has inertial motion. Most things, in fact, don't. Regular life, everyday life, has accelerations and has non-inertial motion. When we drive a car, we have acceleration. When we fly planes, we have acceleration. The Earth produces acceleration on the moon. The Earth itself has acceleration around the sun. Gravitation is the phenomena, because there are other words one can use, but it's the phenomena that governs the universe at a large scale and even a small scale, even on Earth, right? We feel it. So that does not get explained by special theory of relativity. All this stuff has to be upgraded to also explain acceleration and gravitation in the general theory of relativity. That's why special theory of relativity, means a specific case almost. It's like once you have understood properly a more specific special case, especially if it's a case that helps you get a very good understanding of the topic, then you can move on to more general cases, even more complicated scenarios. That's why special theory of relativity is for inertial frames, the more simple stuff, and general theory of relativity is the more difficult topic that covers more general and more types of cases. So that's why special theory versus general theory, okay? So general is harder. One might think, why don't we start with general? Well, because it's more complicated. It's better to understand the special theory of relativity first, because then you understand inertial frames. At least you're good with that. And it's extremely relevant, as I was saying, with E&M. So the entire year of E&M could be taught with a special relativity type of approach, which would get you very comfortable in special relativity. So I think because it also helps with E&M, and E&M is, of course, extremely relevant in so many fields, including by EE, that is electrical engineering majors, I think special relativity is a great place to start with this work. And you might not even need general relativity because, once more, it is to do with gravitation, and everyday gravitation is explained just fine by Newtonian mechanics. So you might not need. So GR is actually an optional class in physics grad programs. You don't have to take it if you don't want to. And so even now, the sad part of that is even now, many, many people don't really understand general theory of relativity very well and struggle with the math of it, including myself. It would be good to be better at it, for sure, because that could help you tackle these more advanced topics. Because if you cannot do the math of something comfortably, then it can be difficult to prove things in that topic or beyond. Because really, it's in the beyond that the research would be, right? Whatever's done already is done already. That's literature review. If you want to do something new, you first have to be very fluent in what's already done. So unfortunately, because GR is complicated math, especially if you're not fluent or practiced in it, it can be difficult to advance the topics that are based on general theory of relativity. So, but the thing I was saying is, why are less people fluent in it? Because they don't need it. Because gravitation is explained fine enough with Newtonian mechanics. Because everyday gravitation is explained perfectly well with Newtonian mechanics. including launching rockets and all that stuff, and satellites and the moon and all that stuff, is mostly just fine with classical mechanics or Newtonian mechanics. You don't really need general theory of relativity, which is the more complete, comprehensive, correct theory of gravitation that we know of so far. But, so that's why they make GR an optional class. But you better be really good at GR if you're gonna further advance it. You know what I mean? So don't be afraid of it. Take it and keep on practicing it with the right professors if you're gonna be wanting to advance beyond the current theory of gravitation, which might honestly be very relevant, such as for understanding dark energy, dark matter, stuff like that, cosmological phenomena, because that's where GR is needed, right? It's at the cosmic levels where you would need to understand general theory of relativity as the gravitational theory instead of Newtonian mechanics. Newtonian mechanics does not help you anymore with that scale. So if you want to do that work and more work with cosmology, I was pursuing cosmology at one point as a subtopic, but then I went into more like particle astrophysics. But if you wanted to do more cosmology, you have to be very comfortable with general theory of relativity. That's why I'm saying this sentence about 10 times now. So please become more familiar and practice it more. And I will too. Meanwhile, experimental evidence began to confirm some of his ideas, raising his visibility within the physics community. Michelson-Morley experiment was repeated, each time yielding the same negative result and casting doubt on the entire ether theory. So remember, the whole thing about ether theory was being disproved experimentally, and then Einstein's relativity theory helped out with the concept of light and how it makes electric and magnetic fields, light is made up of electric and magnetic fields. Meanwhile, experiments on the photoelectric effect confirmed Einstein's equations. One second. Am I reading the right page? Yes, I am. So basically, his work is getting confirmed. Remember how his career was a little bit struggling? So as his work gets more and more confirmed and more people recognize him for his great contributions, of course, that will help him to gain power in the, to gain recognition and authority in the field, which will also help to let him do more work in the field, right? Because if you're a physicist and you have no authority or recognition in the field, it can be very difficult. So furthermore, in 1908, experiments on high-speed electrons seemed to prove that the mass of the electron increased the faster it moved. Oh, God. Right. Mass of the electron increased the faster it moved. Buoyed by the experimental successes slowly piling up, for his theories, he applied for a lectureship. So after his theories were proved correct experimentally, give me 1 second, I need to take off my... So he didn't even have a proper position as a professor, as a lecturer or researcher so far. After his theories are getting proved correct, one by one, he applied for a lectureship at the nearby University of Bern. Because remember, at this time, he has just started his family. He has a young child, a wife, so he's still in Europe and trying to, have a career, make some money, stuff like that. This position was below that of a professor, but it offered the advantage that he could simultaneously continue with his job at the patent office. He submitted his relativity thesis as well as other published works. At first, he was rejected by the department head, Aim Foster, who declared that relativity theory was incomprehensible. His second try was successful. So yeah, the unfortunate thing is when you're very clever and come up with a very difficult to understand concept, no matter how profound it might be, most people will not understand it. and you might not get a job because of it. In 1908, with evidence mounting that Einstein had made major breakthroughs in physics, he was seriously considered for a more prestigious university at the University of, or prestigious position at the University of Zurich. Hey, hi, hello. He faced stiff competition, however, from an old acquaintance, Friedrich Adler. Both top candidates for the position were Jewish, oh, which was a handicap. But Adler was the son of the founder of the Austrian Social Democratic Party, to which many faculty members were sympathetic, so it appeared as if Einstein would be passed over for the position. This is also inspiring, I think, because many of us know what it feels like to be passed over for a position even after doing great work. And it seems like Einstein had his fair share or more than fair share of that experience, which some people might not know about. The problem is with these successful people, people only hear about the successful person after they're already successful. We don't know about their difficulties along the way, right? And Einstein had a lot of difficulties along the way. So it was surprising, therefore, that Adler himself argued strongly for Einstein to take the position. He was a shrewd observer of character and sized up Einstein correctly. He wrote eloquently of Einstein's outstanding abilities as a physicist, but noted as a student he was treated contemptuously by the professors. He has no understanding of how to get on with important people. Due to Adler's extraordinary self-sacrifice, Einstein was awarded the position and began his meteoric climb up the academic ladder. He now returned to Zurich, but this time as a professor, not as a failed, unemployed physicist and misfit. When he found an apartment in Zurich, he was just delighted to learn that Adler lived one floor just below his, and they became good friends. Oh, gosh, I'm happy for him at this time. It is so bad when you're still looking for a job and you can't get one and feels like you cannot sustain your life, In 1909, Einstein gave his maiden lecture at his first major physics conference in Salzburg. Oh, that's right. He did that in Salzburg. I need to visit Salzburg. Wait a minute, isn't he from Salzburg? Was he born there? I'll have to double check. Where many luminaries, including Max Planck, were in attendance. Oh, good. By the way, in academia, it's all about giving the talks. It doesn't really matter how good or bad your work is. If your talk is good, generally you're good. So, yeah, it's extremely important, especially if you've done good work, to give talks as much as possible, because the people in the audience who will attend your talk, that's how they will understand and get to know about you and your work. And with their review and with their blessing, your career can move forward. That is why we have conferences in academia, and it's like mandatory to go to these conferences and to give a lot of talks. A ton of talks. Lots and lots and lots and lots and lots. Too many talks. I have given too many talks. And they take a lot of work to make too. Because nowadays, of course, with everything being, blown out of proportion, it's almost like people just want you to give talks. They don't want you to have any time to do the work. They just want you to give talk after talk after talk at more and more reputable conferences and then nominate you for awards. But if you're busy winning awards and giving talks, when do you do the work, right? That's something that I've struggled with personally. In his talk, The Development of Our Views on the Nature and Constitution of Radiation, he forcefully brought the equation E equals to mc squared to the world. So Einstein was a good orator, by the way. It really helps if you can communicate your science, because some people are not so good at communicating their science, and that is how they're actually behind, and their work is not as known if you don't give talks and cannot communicate your science. So Einstein had this both going for him. He was very clever, very insightful, very productive, at least during that year of 1905 and beyond, right? But also, he gave good talks and he was actually a very good communicator of his work. This is really why he's so famous and successful, even now. He's famous, right? Everybody knows Einstein. That's because he actually did very good with communicating and having relationship with public. Some people, on the other hand, are not so good at that. There are people even now, living people even now, who are less known for their work, whereas a few people are more known. That's because those few people did better job at the public relations and whatnot, and there might have been some sort of a, what's the word, like a notoriety about them, which can help their career. Whereas there are other people too who do good work, but they're just not as well known, you know. Einstein, used to scrimping on funds for his lunch, marveled at the opulence of this conference. He recalled, "The festivities ended in the Hotel National with the most opulent banquet I've ever attended in my life. It encouraged me to say to the Genevan patrician sitting next to me, so this is in Geneva, sitting next to me, do you know what Calvin would have done had he been here? He would have erected an enormous stake and had us burnt for sinful extravagance. The man never addressed another word to me." So he's saying that the banquet was very fancy at this conference, and that makes sense. I have also been probably to my most fancy dinners and banquets at conferences. Like, I've probably had the nicest shrimp at a conference. So this resonates very well indeed. Us academics usually struggle for money, but when we go to a conference and we see all the nice food and fancy arrangements, we do wonder what happened. Einstein's talk was the first time in history that anyone had clearly presented the concept of duality in physics, the concept that light can have dual properties, either as a wave, as Maxwell had suggested in the previous century, or as a particle, as Newton had suggested. So the wave-particle dual nature of light, Einstein gave the talk on that. I wish I was there. Maybe I was in my previous life. Whether one saw light as a particle or as a wave depended on the experiment. So wave-particle dual nature of light, whether you see light as a wave or a particle, depends on which experiment you're doing, my love. For low-energy experiments where the wavelength of the light beam is large, the wave picture was more useful. For high-energy beams where the wavelength of light is extremely small, the particle picture was more suitable. So that's what's so interesting too, is it's really the environment and the type of experiment and the type of observation you're making, which will give you the more wave or the more particle nature of light. So once again, if the wavelength is very big, so like for example, radio waves have bigger wavelength. So radio waves are more like a wave. But if the wavelength of light is small, such as, for example, gamma rays, that's where the wavelength of light is small and the frequency is larger. That's where you might benefit from thinking about light as a particle. So that's what this is about, okay? It's not too difficult. It's simple when you put it like that, right? But that's why we need great scientists to put it like that, to give us the insight after which things become simple. So, but yeah, I sometimes I forget all the names of the different frequencies and wavelengths, but I try to remember some of them. So, for example, radio waves have bigger wavelength than optical or visible light. So I think of it as, well, radio waves are more like waves. They have particle nature, but it's more suitable to think about them as waves, right? And they would also have less energy, right? Because bigger wavelength means smaller frequency and therefore smaller energy. But what's something that I can think of that has bigger frequency and smaller wavelength? Well, gamma rays. So that one might benefit from thinking of it more as a particle, or it will have more particle characteristic or nature than radio waves. And even the detector, by the way, where this is very important, of course, whenever you talk about experiments or observations, you will have to think about the detector that will detect radio waves versus, such as, for example, gamma rays. The detector that you will design, you should keep in mind, are you trying to catch a wave or are you trying to catch a particle? If you're catching a high energy type of light with smaller wavelength, you might want to design a detector that is more like good for catching particles. If you want to design a detector to catch something like radio waves, which is more like a wave nature of light, then you might want to design a detector that is better for catching a wave, such as like an antenna, like a horn antenna would be an example of something that could catch radio waves. Catching to you, good form. Oh, hi, simple boy. Thank you. So, horn antennas is one example of a detector for waves of light, such as radio waves. So keep that sort of thing in mind. Ultimately, if you work in experimental physics, you have to work with detectors, and it helps to understand the fundamentals when you do that. I worked on a radio frequency experiment, and we had a bunch of horn antennas to catch radio waves, actually, coming out of the coming out of the interaction of neutrinos in the Antarctic ice. So in order to detect neutrinos of a particular nature, we had deployed a bunch of horn antennas to catch radio waves as evidence of their interaction in the ice. This is the way of detection of something like a neutrino, which interacts very little, generally speaking, with matter. So you have to get very creative when you try to detect something like neutrinos. So we did this, for example, as an example of a detector for neutrinos. This is one example of making a detector or thinking about what type of detector you need for what type of experiment or detection goal. Okay. Although now a professor, Einstein remained just as bohemian as ever. One student vividly recalled, one second, sorry. One student vividly recalled his maiden lecture at the University of Zurich. He appeared in class in somewhat shabby attire, wearing pants that were too short, and carrying with him a slip of paper the size of a visiting card on which he had sketched his lecture notes. In 1910, Einstein's second son, Edward, was born. Einstein, ever the restless wanderer, was already looking for a new position, apparently because some professors wanted to remove him from the university. Restless wanderer. Wow. The next year, he was offered a position at the German University of Prague's Institution of Theoretical Physics at an increased salary. Ironically, his office was next to the insane asylum. Pondering the mysteries of physics, he often wondered if the inmates were the sane ones. Doesn't surprise me. Sometimes when you're very good at what you do, you make more enemies than friends. Including, he struggled so much to get to these professorships. But even after getting to a professorship and even after doing so much good work, he probably dealt with so much politics at work, So I could understand him moving jobs or wanting to be a restless wanderer, because that's what you are when you don't get comfortable somewhere. Because, first of all, maybe you don't want to be comfortable because you want to grow. And second of all, nobody lets you get comfortable because they're so jealous of your intellect. I don't know. That same year, 1911, also marked the meeting of the first Solvay conference in Brussels, founded by a wealthy Belgian industrialist Ernest Solvay, which would highlight the work of the world's leading scientists. This was the most important conference of its time, and it gave Einstein a chance to meet the giants of physics and exchange ideas with them. He met Marie Curie, the two-time Nobel laureate, and formed a lifelong relationship. Yay! So Marie Curie, by the way, is the only person to have a Nobel Prize in both physics and chemistry. Unless I am wrong, unless there is anybody else more recent, but for a long time, she was the only person who had a Nobel Prize twice in physics and chemistry. The theory of relativity, and also she was the first woman, of course, to get a Nobel Prize in physics, I should mention. There's only like 2 women who have a Nobel Prize in physics, and she was the first. Hi, Molly. Hi, my love. The theory of relativity and his photon theory. So anyway, I'm just so excited that Einstein has met Marie Curie now in 1911 because I'm such a fan of both. So, and I mean, both are such superstars. Everybody knows these names. They're very famous people even now, and famous examples, moreover. So who isn't a fan, right? But it's good when the great meets the great. And it can be rare for the great to meet the great because the great are rare. The theory of relativity and its photon theory were the center of attention. The theme of the conference was the theory of radiation and the quanta. One question debated at the conference was the famous twin paradox. Einstein had already made mention of the strange paradoxes concerning the slowing down of time. The twin paradox was proposed by physicist Paul Langevin, who announced a simple thought experiment that probed some of the seeming contradictions in relativity theory. At the time, the newspapers were filled with lurid stories about Langevin, who was unhappily married and involved in a scandalous romance with Marie Curie, a widow. Oh, good God. Langevin considered 2 twins living on Earth. One twin is transported near the speed of light and then returns back to Earth. 50 years, say, may have transpired on Earth, but since time slows down on the rocket twin has aged by only 10 years. When the twins finally meet, there is a mismatch in their ages, with the rocket twin being 40 years younger. Now view the situation from the point of view of the rocket twin. From his perspective, he's at rest and it is Earth that has blasted off. So the Earth twins' clocks become slower. When the 2 twins finally meet, the Earth twin should be younger. When the 2 twins finally meet, the Earth twin should be younger, not the rocket twin. But since motions should be relative, the question is which twin is really younger? Since the 2 situations seem symmetrical, this puzzle even today remains a thorn in the side of any student who has tried to tackle relativity. The resolution of the puzzle, as Einstein pointed out, is that the rocket twin, not the Earth twin, has accelerated. The rocket has to slow down, stop, and then reverse, which clearly causes great stress on the rocket twin. In other words, the situations are not symmetrical because accelerations which are not covered by the assumptions behind special relativity only occur for the rocket twin, who is really younger. However, the situation becomes more puzzling if the rocket twin never returns. In this scenario, each sees by telescope the other twin slowing down in time. Since the situations are now perfectly symmetrical, then each twin is convinced that the other one is younger. Likewise, each twin is convinced that the other is compressed. So which twin is younger and thinner? As paradoxical as it seems in relativity theory, it is possible to have two twins, each younger than the other, each thinner than the other. The simplest way to determine who is really thinner or younger in all these paradoxes is to bring the two twins together, which requires yanking one of the twins around, which in turn determines which twin is really moving. Okay. You know what? If that was confusing, then I don't blame you. It's okay. The rocket twin accelerated, and that's really not covered in special theory of relativity. We know that. We need inertial frames for special theory of relativity to work. So I was never that interested in this twin story. You know, I always thought of this as a bit of a waste of time that people like to talk about. It doesn't solve any problems. All these mind-bending paradoxes were indirectly resolved in Einstein's favor at the atomic level with studies of cosmic rays and atom smashes. This effect is so small that it was not directly seen in the laboratory until 1971, when airplanes carrying atomic clocks were sent into the air at great speeds. Because these atomic clocks can measure the passing of time with astronomical precision, scientists, by comparing the two clocks, could verify that time beat slower the faster you moved, exactly as Einstein had predicted. Wow. So basically, they were able to confirm this time beating faster, time beating slower the faster you moved thing in 1971. So that is long after all this and long after, his suggestions. So that's what I meant earlier by saying that sometimes when you have a theory or you come up with a theory, it's not really confirmed experimentally until much later. That's okay, Molly. It is confusing. We'll keep going. It'll slowly make more sense. So there are some paradoxes that people like to talk about in the context of special theory of relativity. I would not get too caught up with these paradoxes and these examples that are so famous, because they are just sort of the lore, the stories that people like to tell. They don't necessarily help you to understand the topic. So I would stick with the facts of the topic. And the fact is that special relativity was written for inertial frames. So if you have acceleration, it doesn't really work. And with this time slowing down and faster you move thing, that's just a fact, of the special relativity math and everything. And it was shown with experiments as well in these later years. So just stick with the facts. Another paradox involves two objects, each shorter than the other. Imagine a big game hunter trying to trap a tiger about 10 feet long with a cage that is only 1 foot wide. Normally, this is impossible. Now imagine that the tiger is moving so fast that it shrinks to only 1 foot, so the cage can drop and capture the tiger. As the tiger screeches to a halt, it expands. If the cage is made of webbing, the tiger breaks the webbing. If the cage is made of concrete, the poor tiger is crushed to death. Oh, we don't like that. We want all cats to be safe, even in special relativity. I gotta go because I'm supposed to paint my wall. Oh, wow. Painting the wall might make more sense than this cage experiment. But now look at the situation from the point of view of the tiger. If the tiger is at rest, the cage is now moving and has shrunk down to only 1/10 of a foot. How can a cage that small catch a tiger 10 feet long? The answer is that as the cage drops, it shrinks in the direction of motion. So it becomes a parallelogram, a squashed square. The two ends of the cage, therefore, do not necessarily hit the tiger simultaneously. What is simultaneous to the big game hunter is not simultaneous to the tiger. So that's, yeah, good, good. If the cage, so simultaneity is also relative. If the cage is made of webbing, then the front part of the cage hits the tiger's nose first and begins to rip. As the cage drops, it continues to rip along the tiger's body until the back end of the cage finally hits the tail. Sorry. If the cage is made of concrete, then the tiger's nose is crushed first. You know what? I don't like this. I'm just going to skip to the next paragraph. These paradoxes even seized the public's imagination with the following limerick running in the humor magazine Punch. There was once a young lady named Bright who could travel much faster than light. She set out one day in a relative way and came back the previous night. Okay, oh, so it looks like the rest of the chapter is him getting more recognition for his work with relativity and people starting to sort of understand and appreciate his work. So I think what we'll do is we'll cover the rest of this story for chapter 3 next time and let you go today. I think we've covered some nice things today. And we saw that he got a job and his career is more stable now. There are some other developments that happen in his life, which we'll cover in the next part, in the next reading. And also we'll continue to discuss this work and wrap it up next time. But basically in the following years, he gains more recognition for his work and people start to kind of understand, and some of these paradoxes and examples that I was mentioning from the book kind of help people to understand it, kind of sometimes are confusing too. So it's to be, determined what is really more useful. But one way or another, people started to be a bit more familiar about his work in any case. And that, I think, helped Einstein and helped him to gain more recognition and whatnot. So I think we will continue with this next time. Hi, Jessica. How are you? We will continue this topic and we will wrap up this chapter next time and kind of see what transpired in the years following 1910 and 1911 before we go over to learn about general relativity in the next chapter. So we will start that next time. And we will see what happens in Einstein's life quickly following his special theory of relativity work. We will wrap that up next time because he gains some success, but there's also some other things that happen. We can cover that. Hi there. Jessica says I have a cat named Nala. Aww. That's awesome. Hi Jessica. Hi Nala. Thank you for joining. Oh, hi Superwing. Hi Key. Thank you for reading. Happy evening to all. Happy new week tomorrow. See you next book time. Aww. Oh, that's great. A brown tabby cat. This one is a silver. He's a silver. Ickle, little silver baby. Thank you, Superwing. Thank you, Heike, for sticking around until the end. Really appreciate you guys for being here and listening to the discussion and adding to it in any way you want. We will speak more next time. and I have 3. See, here's my brown tabby / brown tiger. Hi, Sachi Mama. Shonu to. Is a Shonu baby. This one's a Shonu child. Here is Suji. I've got 3 babies here. Thank you once again for being here. Really appreciate all of you. She's a brown tabby cat. I'm back. I was doing some dance. Hi, Kayla. You were doing some dance. Oh, that's very nice. That's very good for you. So Kayla is from England, correct? So I guess it's a little later there. Is it some nighttime gymnastics? Oh, very nice. Thank you, Kayla. Ooh. It's 22:22. I slept 2 days ago while listening. Oh, good. I'm glad it's relaxing. Thank you. Thank you for joining. Thank you for being here. Do check out all our content, videos, shorts. Thank you for supporting the channel. Really appreciate it. Thank you for sharing, liking, subscribing. Appreciate all this support very, very much. Thank you.